So, hi everybody. We restart after a break of 2 weeks. It was a long Easter break. I almost forgot that it's a lecture today because in school it is still the week off, right? So my son is not going to school. Yeah, so one thing, we have 2 lectures left by me, then it's Chiara who will take over, right? And also today, Volodymyr is not available, so I will be also given exercises, maybe in a more advanced, less advanced way than Volodymyr. So I will try to embed some exercise. I have tried to embed some exercises in the lecture, so I will mention them in due course. And then maybe it will be partially on Blackboard also, so old style. Good. So let's try to get back on track, just to recall where we were last time. So if you remember, the whole logic of the course up to now was like this. We started from the topic of dark matter. We first went to the early universe to see, well, maybe how this to get exposed in the dark to the dark matter in this context of the early universe, maybe to see some evidence for its existence, then also to see how it might have emerged in the early, how it was produced in the early universe. Then we went closer to us. We went to look for astrophysical evidence for dark matter. Then we also tried to see what physicists do to detect this dark matter in laboratory or well, in astronomical data. And this was the first part that was sort of really in the sense of the name of the course, Astroparticle physics. So we were trying to learn something about particle physics using maybe cosmology. Then at some point we arrived at this picture. Let's say we wanted to see dark matter somewhere, find dark matter somewhere in the center of the galaxy, of the Milky Way. And then we found that, well, there is a lot of other stuff around, right? So this prevents us from seeing the dark matter signal. So prevents us from doing particle or fundamental physics. But it's a very encouraging picture from astronomer point of view, right? So sort of particle physicists made a detector that is good for seeing various kinds of astronomical sources. And then this is a map of the sky in the energy range above giga electron volt. So for comparison, rest energy of proton is around this, right? So all particles producing photons with energies like this are relativistic particles. So one way or the other, all astronomical objects seen on this map either accelerate particles or are sites of particle interactions, right? Because photons are produced in particle interactions. So there is a lot of sources in the universe or in the galaxy working as high energy particle accelerators and colliders. Maybe this particle acceleration is an important ingredient for understanding of physics of some astronomical sources. So we can also do what people call particle astrophysics, right? So instead of astroparticle physics, people put also accent on astrophysics in this naming, right? So instead of astroparticle physics, we can talk about particle astrophysics. And last time we were discussing some aspects of this particle astrophysics. We looked at these types of sources, well, shown in this. This is one of the most famous called Crab Nebula. This is example of, well, this is the third brightest source in this map. It is here. The first brightest is here. It's of the same type. It is called pulsar, right? So we try to understand what is this pulsar. we ended, I don't know if you have memory, last lecture, we went through several subjects leading us to the pulsar. So we started from some general consideration. Where do these pulsars come from? It happens that they are powered by neutron stars. Neutron stars are born in supernova explosions. Supernova explosions happen at the end of life of massive stars, right? That was the story. I don't know, does it ring a bell? So we looked at some at neutrinos from a supernova explosion. We detected it once from a supernova called supernova 87A. On the left there, it's the image, the optical view of this supernova remnant 40 years after the explosion. Then we looked at bit at the structure of these neutron stars. These are some exotic objects with mass comparable to the mass of the sun, because it was the core of a massive star that collapsed, right? The core of the chunk of the core of the mass comparable to the mass of the sun. So it has it is the mass of the sun squeezed into a region of about 10 kilometers. And by consequence, the density is like 10 to the 15 gram per centimeter cube. What? Well, it's just to refresh the memory, right?
Yes.
Then it also has extremely strong magnetic field. Everything is okay? This was in the lecture, right? The last time. Okay, so let's, and then finally, because of the presence of this magnetic field and rotation, the neutron star powers particle accelerator. It ejects electrons and positrons in the interstellar medium. Then these electrons and positrons produce, lose energy around the neutron star. In gravity, it's somewhere here, the neutron star. So in the interstellar medium, they produce synchrotron, the inverse Compton scattering emission, right? This was the story of the last time. So maybe let me show another aspect of this story. Yeah, this was again small recap of how it worked with neutrino emission. So if you remember, during the collapse of the core of the star, all protons were, more or less, all protons were converted into neutrons. Neutrons were prohibited from decay. That's why we have neutron star. But then, well, these are two reactions. Well, the reaction, the first reaction is the reaction that converts protons into neutrons. So proton plus electron give us neutron plus neutrino. And the second reaction, it cannot proceed. Neutrons do not decay because it needs to return electron to some highly degenerate Fermi gas where all the states in the phase space are occupied. The electron cannot find its place. But, well, what I want to, so an accompanying effect of this is that, well, we discussed this, right? So there is strong neutrino emission associated to this process. And then more or less the medium inside the neutron star is so dense that only neutrinos can escape from the neutron star. So what happens is that when the core of the star collapses, there is a large amount of energy released. We can estimate it as gravitational energy of the star, right? Because when the star was large, let's say initially this core of the star was 10 to the 9 centimeters. So what is it? So 10,000 kilometers, then its gravitational potential energy was small in a sense, right? Then when we squeeze the gravitational potential energy, it's actually minus of this. It goes as 1 over the size, right? So the matter is falling into the gravitational potential well, and the gravitational potential energy is converted into kinetic energy. It hits the medium. This also leads to, this newly formed neutron star should be very hot. It heats perhaps to the temperature about some tenths of mega electron volt, as we see from the energies of neutrinos coming from the star. And then this, well, similarly to the normal star, where photons carry away energy liberated by whatever nucleosynthesis processes inside the star, here neutrinos would take the energy of this order, right? And then, well, this energy will be transported outwards. So I don't remember, did we discuss the explosion itself, or so the neutrino emission is somehow associated to supernova explosion? But we concentrated more on the process of collapse, right? So it was always an inward motion. Then where is the explosion here? This is sort of an unresolved problem in astrophysics. And what people think is that neutrinos play important role in this explosion. So the neutrinos, when they cross the outer layers of the star, they interact a little bit, right? So neutrinos have very small interaction cross-section, something like this. So they can cross large amounts of matter. But even if a tiny fraction of neutrino energy is absorbed through interactions in the outer layers of the star, let's say what people think is about 1% of overall energy contained in neutrinos is absorbed in the outer layers of the star. This is enough to push, to produce pressure on the outer layers and make an explosion. We can make a simple estimate of the power of this explosion. If I imagine that, well, the outer part, if I sketch the star, there is this massive star that had a core that collapsed to form a neutron star. And then during this neutron star formation process, there are neutrinos that mostly cross the neutron star, but sometimes they can interact and deposit some energy. They would be stuck in the outer layers, yeah? So these outer layers, let's say the mass of them is several times the solar mass. And well, if we think that about 1% of the energy of neutrinos is deposited in these outer layers, it would give the energy, which is 0.1 the gravitational energy. I can make a simple estimate what will be the kinetic energy of these outer layers. This gives me an estimate of the kinetic energy of the outer layers of the star. I could tell that this is this mv squared over 2, and I can estimate the velocity with which these outer layers of the star would be expelled. This is the calculation, so I divided this by, let's say, the first approximation, let's divide by the mass of the star. It would give us the velocity scale that is thousands of kilometers per second. Okay. This will be an outward velocity, right? Because neutrinos are pushing from inside. So this is the explosion, because now we reverted the collapse into the outward motion. And as a matter of fact, this will be an explosion which is detonation, deflagration. So this velocity is larger than the speed of sound, the interstellar medium. The speed of sound, just for information, this is about the thermal velocity of particles. If I write something like this, mv square over 2, it's about 3.5 k Boltzmann T. This would give me some estimate of the speed of sound. So for the interstellar medium, it will be some 10 km/s or something, right? So this velocity scale is much larger than speed of sound. So it is a detonation, right? So there will be a shock wave propagating outwards in the medium. And well, just in a case, well, this is an example of a supernova shell. There is a well-defined shell, right? Well, maybe the outer part of the shell is the shock still expanding into supernova interstellar medium, maybe some cascades hundreds of years after the explosion. So why is it interesting for me? Again, I will put this in the context of particle acceleration. Last time we looked at pulsars, right? How did particle acceleration work there? Just to check. What is your memory of that subject? There were two ingredients, right? Magnetic field and rotation. What did this rotation do? This rotation of electrons and protons in magnetic field led to charge separation on the surface of the neutron star and creation of strong electric field, right? We discussed that the potential difference between the poles and the equator can in principle reach 10 to the 20 volt. Yeah, it's like this. If the neutron star rotates with the period around 1 millisecond and magnetic field is 10 to the 12 Gauss. So that was an example of acceleration by large scale electric field. It's like a huge linear particle accelerator operating near the neutron star. Now, there is another possibility to accelerate particles. On occasion, we see that particles are accelerated at the shocks of supernova remnants by a process. I guess Chiara will come back to this process, but well, just to mention this in the context. The process is, well, there is no large-scale electric field here, but the process is more or less has a good mechanical analogy. So if there is a shock wave going through the medium, let's put ourselves in the reference frame of this shock wave, right? So we are moving in the middle of the shock wave. So then we see some, if we are moving with the plasma of the shock wave, we see the interstellar medium falling onto us, right? If we are in the middle of the shock wave, we would see from this side the interstellar medium is pushing, and from the backwards it is the plasma of the expelled matter from the neutron star is pushing, right? So we see if we sit in the middle, we see two convergent flows from one side and from the other side. And this well, The temperature is high, everything is magnetized, so there is magnetic field in these convergent flows. And imagine a charged particle that is moving inside this region of the shock. It would be when it moves forward, let's say, if the shock goes from this direction, if the supernova shell moves from this direction to this direction. So when it goes forward, it will face the interstellar medium. And well, since the particle is charged, there is magnetic field, it would be deflected by this interstellar medium, maybe magnetic field, yeah, inhomogeneities of interstellar medium magnetic field. It would be deflected and turned back. Schematically, we can represent it as it would be scattered, right? When it is scattering, well, yeah, maybe it will be scattered and will bounce backwards. So when it moves backwards, it would see the supernova material impacting on it, right? It would scatter from the supernova material and move back, and so on. It will start moving back and forth between the two media with different velocities. So what happens is that if we think about momentum conservation, let's think that initially the momentum of the particle is mv. It moves with some velocity, right? And then when it will bounce from the medium that has velocity v capital, by momentum conservation, this we know, right? So the velocity will be just reversed. And well, in the reference frame of, maybe I put this, take this. In the reference frame of this medium, the particle moves with some velocity v, and it bounces with velocity v back, right? But if I move to the reference frame of the shock, it would be bouncing with the velocity that is v plus 2 times the velocity of the wall, right? Well, imagine a tennis player when it returns the service, right? If the racket has some velocity, the ball can bounce with velocity higher than it was coming in, right? I can accelerate the ball by impacting with some velocity. Then when it comes back to the other side, there is another tennis player with the racket with some velocity, right? Bouncing ball back. And well, if we imagine that, well, if we think, well, do some calculation like this. So from this formula, I can derive that the change of momentum over the momentum itself is about velocity of the wall or of the medium divided by velocity of the particle, right? So at each bounce, there is an increase of momentum of the particle. Contrary to the tennis players, there is no air between the two, right? So in the tennis game, it is the drag by air that decelerates the ball, right? So at the end, they reach some, well, the tennis match reaches some steady state velocity scale, maybe 100 kilometers per hour, right? When we look at the, well, how they measure the speed of the ball. So it's typical to have 100 kilometers per hour. It doesn't go, it's not a runaway process. If you imagine that the service lasts for a long time, if it would be in vacuum, the velocity would be increased in a runaway manner, right? But well, that's what happens here. There is no medium to stop particles in between. So every bounce, the momentum grows by this fraction. If we imagine that it takes some period of time, delta t, to go back and forth, so we can tell that the momentum grows as at the rate of delta p over delta t, which is proportional to p itself and the velocity of the medium, right? Of the shock or of the medium, which is about the same. If we integrate this equation, we understand that the momentum of particles is expected to grow exponentially as long as they reside between the two media, right, in the shock region. Do you follow me? So the longer we keep particles in the shock region, the larger is their energy. But of course, well, this is the bouncing force and back is a random process. So at some point, particles can be lost from the shock region. We can imagine that the probability to escape at every time, at every bounce, is also some exponential function because, well, there is some certain time scale of escape. If we keep particles for long, more and more particles for a long time, more and more particles would escape, right? So if I combine these two formula, at every bounce, the energy grows exponentially, but also the number of particles decreases exponentially with some other exponential time scale. I can calculate how much particles do I typically have per unit energy, just like this, on average, right? Dividing dN over dE. And this gives me some spectrum that is sort of power law in energy. I will have, well, some particles that live for longer and longer in the shock region gain more and more energy, but the number of these particles is decreasing with energy, right? Because some particles escape. So at the end, I expect to see particle distribution. Yeah, the particle distribution will be something like dN over dE, proportional to the energy to some power, is gamma, whatever, right? This is a power law type spectrum. So that's what we see in the supernova remnants. This is an example. I see this is an image of a supernova remnant in TeV gamma rays, taken by a telescope that is called HESS. So this is the measurement of the spectrum by this telescope HESS and telescope Fermi. And well, we see that first of all, the energies of particles in this supernova remnant reach at least some, well, this is 10 tera electron volt. Then we see what we see in this picture is, maybe I show the exercise, right? So maybe let me explain the exercise and the picture. So what we see in this picture is emission from electrons accelerated in the supernova remnant shock. And we see two types of emission. So on the left, well, this is a model and some data in X-rays and in gamma rays. So this bump in the spectrum is synchrotron emission from electrons. The second bump is called inverse Compton scattering. You've seen perhaps some of this somewhere in the course of electrodynamics. Yes, no? This, the synchrotron emission, it is emission from electrons gyrating in magnetic field. The formula for the energy of synchrotron photons is like this. It depends on the energy of electron. It depends on magnetic field and of course on the charge of the particle, right? So this is, well, I did the numerical estimate for this formula for typically magnetic field 10 to the minus 5 Gauss, which is typical. Well, we will estimate this in the exercise. I expect the emission to be in X-rays if electrons have energies about 100 tera electron volt, something like this. So, and we see emission in X-rays here. So we know that there are 100 TeV electrons. Then well, the second bump is Compton scattering process. This is when energy electron meets low energy photon, for example, from stellar light that is present everywhere in the Milky Way galaxy. So this process would, the electron would kick the photon and give some fraction of its energy to the photon, converting it into gamma ray. There is also a formula for this. The energy of the upscattered gamma ray is related to the energy of initial photon through the gamma factor of electron square. We can also use this formula to understand, to find again that these electrons with energies reaching 100 TeV, they produce synchrotron here and Compton scattering here. Okay? Then we see that above some energy, the spectrum of emission quickly goes down. This is because there are no particles with energies higher than 100 TeV maybe in this source, right? But below 100 TeV, we see a spectrum that looks like a straight line. So we understand that this inverse Compton emission at energies lower than this maximal energy is produced by electrons with smaller energies, right? The low energy photons that are upscattered, they are always the same, but there are electrons with different energies. They produce Compton scattering at different energies in gamma rays, right? So all these photons are produced by electrons of smaller energy. I can deduce from here that, let's say, if this would be emission from electrons of 100 TeV energy, if I decrease, if I go down by 4 orders of magnitude in energy, say from here to here, I understand that I need to decrease energy of electrons by just 2 orders of magnitude. So from looking at this plot, I already see electrons with energy forming maybe a power law spectrum with energies between TeV and 100 TeV, right? Between 10 to the 12 and 10 to the 14 electron volt, right? So this confirms us that we see this process of particle acceleration and formation of high energy particle spectrum that is power law. From this data, I deduce this information. And more generally, so here we see electrons shining. We also think that if electrons are accelerated, there is no reason why protons would not be accelerated by the same process, right? The only thing is that we don't see these protons because if we look at the formulas, maybe let's look at the formula, this one. So this is the power of synchrotron emission. This is another formula that you should have seen in the course of electrodynamics. But for a reminder, it's here. So the power of synchrotron emission scales as magnetic field, scales as the energy of the particle, and also, well, there is a mass of the particle in denominator. Now, electron has the mass half, rest energy half mega electron volt, proton is giga electron volt, so the difference between the masses is factor 2000, right? If I put 2000 to the power 4, it's a tiny, well, in denominator, it's a tiny number. So this means that I would never see synchrotron emission from protons in this source. I see this at this level, synchrotron emission from electrons. The power of synchrotron emission from protons is by a factor of this 2000 to the power 4, 10 to the 13, smaller, right? So it's a tiny flux, not detectable by telescopes. Same would be for inverse Compton scattering. It's difficult to see protons interacting. Still, we see them in some sources. I will not go into this subject, but in general, we think that protons are accelerated in the same way as electrons in these supernova remnants. So this brings me to this plot. We can, well, people tend to think that most of the cosmic rays in the galaxy, if you remember, I've shown this spectrum of cosmic rays in the very first introductory lecture. I told that we detect cosmic rays with energies from giga electron volt up to 10 to the 20 electron volt. So now I come back to the subject, and well, the hypothesis is that most of the bulk of the cosmic rays in the galaxy, starting from giga electron volt, maybe up to the energy of 10 to the 15 electron volt or something, is coming from supernova remnants from this shock acceleration process that I described a couple of slides before. Good. Yeah, maybe one thing that we would understand if we do the exercise, I put here a question. What is theoretically the maximal possible energy of particles that could originate from one or the other type of astronomical source? We will do this part of the exercise to understand that perhaps the supernova remnants would not produce cosmic rays with energies much above this, let's say, electron volt 10 to the 15 electron volt because of some limitation of the source configuration. By the way, this limitation would be valid also for the Large Hadron Collider in CERN. It would never produce particles with energies above certain limit just by its geometry, by construction, right? So we will try to understand why is this like this. So this was the end of the story of supernova. Well, maybe, well, if I look at, it was my small presentation, a small part of the course on sources of gamma rays that we find in our Milky Way galaxy, right? So we saw pulsars, the previous lecture. We see some supernova remnants. I would have a difficulty to spot one clean supernova remnant without pulsar on this plot, but they all line up along the galactic plane. Maybe 5. So I'm about to switch the subject. Maybe we do a break now, or it's too early for a break. No, it's okay. It's okay, yeah. So I would switch subject now. I would rather, well, discuss two related things. So we think that cosmic rays with energies from GeV to PeV are coming from galactic sources, from the supernova remnants. Maybe if we talk about electrons and positrons, they may be coming from pulsars. But, well, the sources of cosmic rays in this range, they should be different. We think that they are related to some sources, or maybe they are related to some sources that are out of the galactic plane. That would be called active galactic nuclei. So in this Fermi-Lat map, most of the sources out of the galactic plane are of this type. So we can try to understand what kind of sources are those. So let's make a break of 10 minutes, right? We come back at 9:07, or let's round it up to 9:10. Okay. Quiet today.
C'est ce que je fais tout le temps. C'est pas une technique approuvée par et genre, mon cerveau, il me trouve toujours d'essayer de trouver cette affaire. Du coup, je passe mon temps à faire quelque chose, genre, ça, c'est parce que moi, j'aime pas. En fait, l'année dernière, en échange, j'avais plus de temps. Je vais courir après, là. C'est du coup, une dame, c'est bon. Moi aussi, je vais courir. Ça, mais tu vas... Avec moi. Pour dire que ça va pas le faire. Ouais, il y a même
Okay, so let's restart. Then, as I told, we will try to understand what kind of other gamma ray sources do we see in this map. These are the sources out of the galactic plane. Sometimes they look as beautiful as pulsar wind nebula. We looked at Crab nebula. This is an example of the near active galactic nebula called Centaurus A. It looks like this on the sky. Try to understand why is it this appearance, yeah? So maybe the first thing to notice is that we identify these sources with supermassive black holes. Then maybe the first, before we go to, sorry, yeah, it's okay. So yeah, with supermassive black holes, let's first try to see what are these things that we are dealing with. Before going to active galactic nuclei, let's try to understand what are the nuclei of galaxies. Let's say, let's start from our own Milky Way. We do find a supermassive black hole in the Milky Way in our own galaxy. I don't know why is it double it's written like this, but we find it in the source that is called Sagittarius A. So in constellation of Sagittarius, the star marked A hosts a supermassive black hole. This is an image of the very center of the Milky Way, somewhere around here. The plane of the Milky Way is here, and on occasion that the previous slide was the gamma ray image. This is radio image. It also knows something about high energy particles, by the way. If I come back to this plot, you remember the gamma rays would be partially originating from this Compton scattering process. At lower energies, we find synchrotron emission also for this supernova remnant. There was a radio point here. Radio photons have energies 10 to the minus 5 electron volt or something. So this is part of the synchrotron emission, and also everywhere in the Milky Way. This is, for example, Sagittarius A itself is a source that appears supernova remnant-like. We don't know what is the nature of this source, but it's a bubble that emits synchrotron emission. And this is how it looks like in the radio band. By the way, we see a lot of other radio features. You see some features even like this, right? This is a strange things. These electrons moving along ordered magnetic field in the galactic center region, right? So electrons spiraling along magnetic field lines. and emitting synchrotron emissions. So somehow they trace the geometry of magnetic field in the galactic center. So if we concentrate on this bubble that is Sagittarius A, somewhere in certain location in this bubble, we find a source that we don't see, but we know that this is something very massive. How do we know this? Let's say this is an image in the infrared band. The size of the image, well, let's not concentrate on this, but well, this source Sagittarius, the center, well, this part of the Sagittarius A called Sagittarius A star, for whatever reason, is somewhere here. We don't see the source in the infrared band, but if we look at the stars moving in the galactic center region, we see that they all turn around a point. They move sort of along elliptical orbits around some center that we don't see. But even if we don't see what is the object, we can still derive its properties, right? From just Kepler laws, from Newtonian mechanics. We know that, well, like in the solar system, the planets are moving along elliptical orbits with the period that depends on the distance to the star that gravitates, yeah, and the mass of the star. So here, if we measure the mass of the object around which everything rotates, we will find that the object is sort of 4 million solar masses. Some invisible object that is 4 million solar masses, and it is compact. The star with the most compact trajectory approaches the object on the distance that is 10 to the 3 times some characteristic distance size length scale for a black hole. I write it down here. I don't know, how many of you did follow the general relativity and cosmology? Maybe, yeah. So you have seen, right, this scale. It is called gravitational radius. Maybe a simple way to understand it without general relativity would be like this. If we take a massive body, we consider circular orbits around this massive body. We write the second law of Newton. And we tell that, well, we are interested in the circular orbits, right? So the acceleration is centripetal. And then we derive from this the Keplerian velocity. This is valid for planets in the solar system, for stars rotating in the disk of the galaxy and so on. We have seen this formula many times, right? What we can also derive, some additional fact that we can derive from this formula is that if well, we approach the center of gravity, the velocity grows, right? At some point, it will grow to the speed of light. If I write like this, E square equal to C square GM R, I can derive some R, let's say some distance scale that would be GM over C square, right? So by construction, this is the distance at which the rotation velocity is the speed of light. So if I launch a photon at this distance in the direction tangential to the circle, right? So the photon would go along the circle. We can imagine that, well, I stand on a planet that is there. I shoot I take a pocket light, right? I shoot the pocket light in direction perpendicular to the direction to the star, right? So the light will come back to me. Well, it will circulate, right? So means that the light would not escape to infinity at this distance. That's the origin of the term black hole, right? So this is an object where the gravity is so strong that it would not, that the light would not escape, yeah? So if I look at the trajectories of stars in the galactic center region, if you go to YouTube, or you go to Google, you type galactic center movie, it would make you the time lapse. So this is real data. You can see them also in time lapse. So we see that the stars are orbiting an object of this mass within the distance that is 10 to the 3 times the gravitational radius of a black hole with the mass 4 million solar masses. We understand that, well, whatever type of object we imagine, well, if the simplest object in a sense is a black hole, because if we try to imagine an object that is not a black hole, say a cluster of neutron stars or something like this, it can be invisible in telescopes in this case. But then we do some dynamical study. We understand that well, the cluster of neutron stars would collapse to a black hole, and of this parameter, well, we have 4 million neutron stars squeezed into a distance. We can quickly estimate this is 1.5 times 4 million kilometers, right? They would bump into each other. They would finally collapse gravitationally. So we understand that by default, the object that is in the center of this image is a black hole, right? It is a supermassive black hole. The term is reserved for this sort of objects to distinguish them from another type of black holes that we find abundantly all across the galaxy. If I come back to this very first part of the lecture, to this gravitational collapse story, if you remember, there was this core of the star that is collapsing, but then the neutrino pressure was strong enough to expel the outer part of the star. It is not always like this. If the outer part is more massive than some limit, then the neutrino pressure would be not sufficient to expel the outer part, right? Because the inner part that collapses is always some fixed mass. Well, I didn't mention this at the beginning. The last time when we had the lecture, the gravitational collapse starts at some limit that is called Chandrasekhar mass, just in case, right? So the amount of energy liberated in neutrinos is always the same. It is fixed, right? But then the outer part of the star, it can have whatever mass. So if the mass is too large, the neutrino pressure would be not sufficient to expel, or supernova explosion would fail, or maybe partially fail. So there will still be some matter that would ultimately fall onto the surface of the neutron star. And if you remember, well, just a flashback, the neutron stars, they have maximal possible mass. That is on this picture, it would be somewhere, well, several times the solar mass. This happens, well, the neutron star would collapse to a black hole when it reaches certain mass scale. That is the analog of Chandrasekhar mass. You remember in the Chandrasekhar limit, it was the pressure of the gas of electrons that was failing to resist gravity. So the neutron star, the pressure is given by the gas of neutrons. At some point when the star is too heavy, it would fail to resist gravity, it would collapse to the black hole. We find a lot of black holes of small mass, about 10 solar masses in our galaxy. I will come back to this subject next time also, by the way. But, well, this object in the center of the Milky Way is not of this type. 4 times 10 to the 6 solar masses is too heavy for a black hole to be produced in the collapse of a stellar core. We find stellar mass black holes produced in collapse of the cores with masses maybe up to 100 solar masses, right? But never millions of solar masses. So it's some new type, another type of astronomical object. By the way, we don't know where do these supermassive black holes come from. We don't understand the process of their formation. So it's one of the unresolved problems in astrophysics. But, well, this is in our own Milky Way galaxy. Otherwise, if we look at this object, I told it is barely visible in radio. It is not visible in infrared. In X-rays, our black hole here, sometimes it does something interesting. Most of the time it is invisible, but sometimes it does some, well, people call this outbursts. Sometimes there is a source appearing at the place of the black hole and then disappearing in one day, maybe once per year or once per several years. So it's a strange object. In gamma rays, maybe if we do an exercise, well, I don't know which exercise we will focus on after the lecture, we can look at the map. In Fermi, we can look at Fermi data. There is an object in the galactic center. By the way, well, it may be related to the black hole. And by the way, it is on occasion at the same places where we would find the dark matter signal, right? So we started the whole story of looking into gamma ray data because we wanted to see a source in the center. There is a source in the center, but how do we know? Maybe it's a black hole that is shining in the center and not the dark matter. So it's another sort of nuisance thing, the background for the fundamental physics research, but it may be the black hole source in our galaxy. We don't know. But mostly our own galactic supermassive black hole is an unremarkable source. In any case, even if we take, well, this gamma ray source is sort of the brightest across wavelengths for this black hole, we would see that this is a bit underestimated. It would be 10 to the 3 times the solar luminosity. So the sun is 10 to the 33 ergs per second. The source in the galactic center integrated across all energy ranges, it's 10 to the 36 ergs per second. It's unremarkable source because if we think about stars, the brightest stars have luminosities about 10 to the 38 ergs per second. So still factor of 100 larger, right? It's a smallish source. Then we call it quiet galactic nucleus, right? Sometimes the galactic nuclei, for some reason, which we also don't understand very well, they become active. When they become active, we witness this in this way. So let's say the first time when we start seeing that the galactic nucleus is active, it comes like this. So this is, for example, an image of a galaxy, like our own Milky Way. It's a star-forming galaxy. We even see the disk of the galaxy. And we see in the center of the galaxy sort of a source that is brightish. Yeah, it's not like completely unremarkable, like our black hole in the center of our galaxy. And it is a strange source. If we look at the spectrum of this source, we see something like this. So this is the spectrum in the visible band. Just in case you recognize, perhaps there is a continuum emission, and there are peaks like this. This would be, what is this? Emission lines, right? Sometimes, well, first of all, this is already, if we think about stars, it's quite untypical for stars to have emission lines. We typically see absorption lines in the stars. The absorption lines, the thermal radiation of the star, when it passes through some material at the outer layers and the atmosphere, this material would block some part of the continuum black body emission, right? So this would be absorption lines. Here, it is emission lines, and the emission line pattern is really weird. What people do in spectroscopy like to do, they like to match the energies of the lines to the reference energies of lines produced by some elements, right? So we would do this. We can, well, that's what is done on this plot. So there is some carbon, magnesium, and stuff like this. So we can surely identify the energies of the lines, but well, some of the lines are really weird. You see here, this is a line that is at its reference energy, and it is a narrow peak. Well, perhaps the spectrometer is quite good, right? So the spectral resolution, the uncertainty of the measurement of the energy of the line is monoenergetic, right? Normally, but the energy of the line is measured quite precisely. But suddenly the spectrometer gets bad just next to that line, right? So this is a broad line. It's not a bad quality of spectrometer measurement. It's just the line itself is broad. What is the explanation? Why we would see broad lines? The lines can be shifted toward red or toward blue if there is Doppler effect in action, right? So if something is moving toward us, the frequency would be increased, right? So the wavelength shortened, it's a blue shift. If something is moving away from us, it would be a red shift. The rule of the Doppler effect is something like the shift of the reference position of the line is given by the velocity along the line of sight, okay? So what I can deduce from here, if I look at this, well, I can really measure the width of the line here, yeah? I would see that something is moving with, well, maybe up to 10%. The width of the line is 10% of the line wavelengths itself, right? So something is moving with velocity up to 10% of the speed of light in this source in the center of the galaxy. This is one thing. So I don't know, if I come back to this Keplerian formula, what can be moving well, the line is broadened, right? So something is moving both toward me and away from me. Maybe something is rotating or something is moving around some gravitating center. If I come back to this formula for Kepler velocity, I understand that if I want to move with the speed 10% of the speed of light, I need to be at the distance that is at most 100 times the gravitational radius, right? So this is like this, yeah? So it's a compact source, like we find the stars moving close to the black hole. Here we find some matter moving close to some object within 100 times its gravitational radius, so 100 times the size of a black hole with some mass. Then another property that we see, these lines are also changing in time. Like I told, in our galactic center, the X-rays are sometimes flaring. So the source is changing. There the lines are changing in time. We see that sometimes they vary. They can appear, disappear, or change shape on the time scales of months, right? We can deduce some information on the size of the source from this. It's just called causality argument. I don't know if it's intuitively simple or not. Imagine that, well, this line is produced in a source of the size like this, yeah? It's a disk perhaps, right? If I want to switch off the line from all parts of this disk, right? So I want to switch off the source. So let's say I have people with turning off the light here and turning off the light here, right? But they need to do this simultaneously, more or less, right? How do they do this? They tell one person here tells that I switch off the light, yeah? And it switch off the light. So then the other person need to do this simultaneously, but it needs to hear well, the command, right? Switch off the light, right? but the comet cannot go faster with the speed faster than the speed of light from here to here, right? So if I see that they manage to switch off the light simultaneously within the time range of some delta t, right? So I know that the size of the source cannot be larger than c times delta t. Do you follow me? So it tells us that the source is compact. It's actually some maybe 100 astronomical units. Astronomical unit is the distance from the size from the Earth to the Sun, right? Based on this measurement. So if I compare the two measurements, I understand that well, my source is like this. I have matter moving with velocity of this up to 10% of the speed of light, so close to the source within these distances. I can deduce that the source around which the matter is moving has to have mass of about 10 to the 8 solar masses. About some millions or hundreds of millions of solar masses, right? From these two measurements. So we see, well, in fact, like this, we can see supermassive black holes in other galaxies. Contrary to our galaxy, this black hole is bright, right? We see that the luminosity of the central source is sort of already comparable to the luminosity of the host, the entire host galaxy, because we see the source from far away. So we know that on occasion, the black hole in that galaxy is active, okay? Our is inactive or dormant supermassive black hole. That one is active. Now, what can be the source of this activity? Let's try to see. Yeah, maybe to give you some idea of how it should look like if we would be there. So these emission lines would be some clumps of matter moving not very far away from black hole. They are represented by these bubbles of different color. Sometimes, well, we imagine that in the center there is this black hole, and then the continuum emission here would be coming, well, we need some continuum light source. We would think that, well, this is matter moving close to the black hole that produces this continuum emission, illuminates these clouds, and then we see these clouds variable, well, this line emission variable because the cloud configuration is ever changing, right? So something like this. People also add some additional component here, like a torus that is blocking the light. This is because sometimes they see sources with lines that are only like this, narrow lines. Sometimes they see broad lines. So we understand that the broader lines are produced by clouds moving closer to the black hole. Yeah. Then sometimes we see broad lines, sometimes we don't see broad lines. This means that sometimes we observe the source from some direction where the light from close by the black hole is blocked. Sometimes we see it from the direction where it is not blocked, something like this. So there is some phenomenology of this. The geometrical picture of this active black holes emerges from some piles of possibilities for observational appearance of this active galactic nuclei, so supermassive black holes that shine the light. Maybe to tell something about this bright source, I've seen the picture of it when I was taking coffee. I saw this picture on your back.
Oh.
Right? Where does it come from?
It's the physics section subject.
It's the EPFL physics section. So this is the well, the picture of the EPFL physics section. So this matter moving around the black hole, why would it be shining? The idea would be sort of the same as I told this story of neutrino emission, right? So when matter was collapsing, squeezing, well, falling into the gravitational potential well, gravitational potential energy was converted into kinetic energy. So kinetic energy, when it is redistributed between particles, it heats, it means that the matter heats, right? So the velocities of particles grow, the temperature grows, right? And here in the collapsing core of the star, nothing was shining light because photons would not escape from this collapsing core of the star. The core is too high density, right? So the mean free path of particles is much shorter than the size of the source. On occasion here, the process would be the same. If matter is falling into the black hole, gravitational potential energy is converted into kinetic energy, redistributed between particles. So matter moving closer to the black hole is hotter. When it gets hot, it starts to shine as black body. It is always shining as black body if it is dense enough, right? So we can quickly, oh, by the way, I forgot to add this. We can estimate the temperature of matter moving close to the black hole. But on occasion, what I did here, I told that let's see for every particle that approaches the black hole, when it approaches by the distance r, the energy converted, the gravitational potential energy that should be converted into kinetic energy is something like this. I can re-express it as, well, I can separate the combination that is the gravitational radius. So it's the rest energy of the particle times the ratio of the gravitational radius to the distance where the particle is moving, okay? So from this formula, it is easy to see that when we throw something into the black hole, if the particle is already approaching the black hole, a good fraction of its rest energy is converted into kinetic energy and into heat, right? This heat can be dissipated through radiation. So this process of matter falling onto the black hole is a machine to extract energy from gravitational potential energy with called with efficiency that is like this, Rg over R. So maybe it's a good way to extract energy from matter, right? If we think about power plants, say nuclear power plants, they extract mega electron volt, the binding energy of atomic nucleus per atomic nucleus, which is say giga electron volt, right? So the efficiency is 10 to the minus 3. Here, if we dump matter into the black hole, we would be extracting energy, getting heat out of this process with efficiency of about 1. Yeah? So if we manage to build a power plant based on this, it would be a good, it's ecological, right? Because there is no bad things coming out, right? Only heat, maybe in the form of radiation. We would boil water, produce electricity from this and so on. We don't have black holes around, so that's the only problem, but otherwise it's a good source of energy. So then if, well, I can also use this formula to tell that, let's say, if I'm approaching the, by the distance of 10 times the gravitational radius, I can calculate the overall luminosity of the source. Here is my estimate. For every particle, I get 10% of its rest energy out, yeah, in the kinetic energy and maybe then in the radiation. If I throw, say, some mass per unit time, if I throw matter at some rate, I can estimate the luminosity of the source. This would be 10% of the rest energy of the falling matter, right, per unit time. This would give me some enormous luminosity, depending on how much do I throw, but it's very typical for a supermassive black hole to absorb something like solar mass per year. I throw one sun in the black hole per year. It would give me 10 to the 45 ergs per second. again, if we compare with the solar luminosity, which is 10 to the 33 ergs per second, this is 12 orders of magnitude larger. So it can be a very bright source. I can even compare it with the luminosity of the entire Milky Way. The Milky Way luminosity, well, the Milky Way has something like 10 to 11 stars. So its overall luminosity is 10 to 11 solar luminosities. This is larger than this. So the source here, well, let's say this example is a moderate source, right? Otherwise, depending on how much this black hole absorbs per year, the source can even outshine the whole galaxy. And this really happens. So sometimes we see these sources like this. When you see, well, this is when you see this sort of lines here in the optical image, this means that the source is not resolved by the telescope. We see some defects of the optical system, right? For a galaxy, we see nice images that because they are resolved, right? So the optical system is, the defects of the optical system is not, the aberrations are not amplified, but the point source would look like always like a star here, right? So at the first sight, we see a source that is like a star, but with the spectrum that is weird with these sort of features, right? That are not typical for the star. And well, the first name, well, the idea, here comes the idea of the name of these sources. They are called quasi-stellar objects. This is a certain type of active galactic nuclei with luminosity that is larger than the luminosity of their host galaxy. Okay? So then only if we block the light from the source, it's a point source, right? So we can block the part of the detector plane where the signal from, well, let's say we put a mask on a telescope to block the light from the source. We can see that this source is sort of similar to this one. It's only the central source is so bright that we didn't see the galaxy host in the source in the first approximation. But if we block the light from the source, we see the host galaxy also, right? So this source and this source, they are of the same type. Yeah? So quasi-stellar objects are also active galactic nuclei. On occasion, this type of sources where we do see the host galaxy, and the host galaxies of certain type, we call them Seyfert galaxies for the person who first found this effect of broad emission lines. It was Seyfert. Okay, so on occasion, I will not go into the details. Why is it like this? The black hole effect. Well, this is a general feature is that normally nothing falls spherically symmetrically into some object, right? It has angular momentum. So if matter has angular momentum, it would rotate and it would tend to form a disk because the centrifugal force would stop infall in equatorial plane while it is not active in the along the axis of rotation, right? So the matter would preferably collapse faster along the axis of rotation than along the equatorial plane. So so it would form a disk, and then just in case on this picture, we see this effect of light being deflected, right? I told you that if we approach by the gravitational ray, the light would even circle the star, right? So we see the back of the disk because the light that was emitted, well, from our point of view, if we go to the back side of the disk, the light was deflected and went to us. So we see the surface of the disk even behind the black hole. That's the explanation of the effect. And we see also, by the way, the other surface of the disk that for the photons that went around the black hole from below. Nice. I didn't know that this is the advertisement for the physics department. Okay, so maybe now, well, I want to relate, well, this was my explanation of what kind of objects we see are these active galactic nuclei. now I come back to this picture. You notice that up to now, I explained some stuff that does not hint me that I should see those black holes appearing in the gamma ray map, right? To appear in the gamma ray map, the objects need to accelerate particles. And up to now, it was matter falling into the black hole, doing some, producing some heat that is dissipated maybe in the form of black body radiation. So this does not involve any particle acceleration. Yeah. Now, remember in pulsars, the important ingredient was that pulsars rotate, there is magnetic field, so there is a machine, dynamo machine, or say unipolar inductor machine or electric generator that was generating voltage because of this, right? So we need to find some additional ingredient, physical process that would lead to appearance of this active black holes on the gamma ray map, right? So particle accelerator should be operating there. Let's say here I would a bit disappoint you. We don't know why is it like this, but some part of this, we really see that only some small part of the black holes in active galactic nuclei decides to operate particle accelerator. It is about 10% of them that do this. We suspect, we think now, right? So this all may be wrong, but this is an observational fact. There are some competing models. Why is this like this? But no clear understanding. And we naturally divide those. So when we cannot explain, we just do phenomenological classification. We tell that these black holes that don't accelerate particles, we call them radio quiet. You can guess that in radio, we see synchrotron emission. Synchrotron emission is from accelerated electrons. So when there is no radio, no synchrotron emission, no accelerated electrons, so they are radio quiet. Otherwise, black holes that do accelerate particles, they are called radio loud. So we can measure something about, learn something about particle acceleration process in these black holes. And when they decide to accelerate particles, they do it quite spectacularly, let's say. This is how, I will come back to the scheme on the left. So we can already see the difference between scheme on the bottom part of the picture and on the top part of the picture is in this feature, right? This feature is called jet. This is the flux of relativistic electrons and positrons. That's what we think it is. Or maybe there is something else, but we see electrons with some energies that are again reaching some much above the energies that we find in Large Hadron Collider, right? So something like this. Why is it a directed outflow of particles? We don't know exactly, but observationally it appears like this. So this is an example of active galactic nucleus that is radio loud, not very far from us. This is the galaxy called M87. It is a galaxy into which we will ultimately fall. It's the center of a galaxy cluster next to us. We are perhaps gravitationally bound to this galaxy cluster on the time scale of some tens of billions of years. We will be approaching this galaxy. So otherwise, on the sky, if we look in the optical band, it is an elliptical galaxy. It's not like our Milky Way, but it doesn't matter. So the galaxies can be spiral or ellipticals. This is an occasional elliptical galaxy. Again, in the center of the galaxy, unfortunately, this is saturated, but we see a point source that we can identify with perhaps this supermassive black hole. And then on top of this, we see a feature like this. It's apparently very easy to see if you have a decent, even amateur telescope. The feature was discovered in 1918, occasionally by some astronomer, name was Curtis. He reported in an article a curious ray in a cloud. Notice that in 1915, 1918, people didn't really understand that the galaxies are galaxies. For them, they were clouds on the sky. So he found that in one of those bright clouds on the sky, there is a linear feature, a curious ray, right? And that's it. So maybe he was already able to measure the spectrum of this, right? So it is shown in blue here. This is because in this galaxy, all the stars are like the sun. So they have some typical spectrum that makes the galaxy a bit red in appearance. And this has a spectrum that is has a lot of blue light. So the spectrum is really different. This is because, in fact, this is synchrotron emission from these relativistic electrons, as we know today. But at the time of discovery, it was a puzzling feature that nobody has an idea what can it be, right? And it was the only one observed at the time. Now, today, we see a whole lot of beasts like this with whatever spectacular appearance. This is a sample of them. This is this nearest to us, active galactic nucleus like this. So here we see some details, right? This is, well, again, there is perhaps an elliptical galaxy behind. There is this dust lane. It might be a rest of, sometimes galaxies collide and merge. So this galaxy is in the process of merger. So again, there is a central source. There is a jet. On occasion, we see that it is two-sided here. There it was really one-sided. There is nothing on this side, right? Sometimes, well, these jets are looking like this. So notice that this is the galaxy, an elliptical galaxy. So the size here is maybe like in the Milky Way, it's tens of kiloparsecs, whatever it is, kiloparsec. You know, you don't have a feeling, but well, let's say the tens of kiloparsecs is a typical size of galaxy. 1 kiloparsec is 3 times 10 to the 21 centimeter. So it's in whatever sense, right? But the distance to the next galaxy from us, next distant galaxy from us is Andromeda. It's megaparsec, right? The distance to M87, to which both we and Andromeda are perhaps fallen, it's about 20 megaparsec, right? Then here, this is the elliptical galaxy, so maybe tens of kiloparsec, and the jet is, well, stretching through, well, out of the galaxy. Sometimes these jet features, they reach megaparsec scales. So some highway with, well, maybe if we imagine, put it on our scale, there would be a highway from us to Andromeda galaxy, which is straight. You see that, well, they are really straight, right? So maybe to understand what are these beasts, I will not tell today how they formed, maybe some features of them. So if I come back to this M87 galaxy, I see this jet in the visible band already since more than 100 years. So maybe since 50 years or so. We can also trace these jets in the radio band. All these images here, they are in the radio. And also in M87, this is the same jet seen in the radio. We also see that it goes out of the galaxy and then dissolves, well, wraps around the galaxy, dissolves in the intergalactic medium. But then what is interesting with radio telescopes, we can get angular resolution, well, a very good angular resolution that is not available with optical telescopes. So we can trace the jet down to its origin, which would be, we think that this is the location of the supermassive black hole. And on occasion in this M87 galaxy, since a couple of years, we really see the supermassive black hole there, because this is a very, this is largish black hole by supermassive black hole scales, it has 10 to the 10 solar masses, more or less, 10 billion solar masses. So when it is large in mass, it is also large in size, because the size is proportional to the mass, right? So, and it is not very far away. So if we estimate the angular size of the black hole, if I have a source of the size r, I'm looking at the distance d, I can estimate this angle theta with which I should see this. It would be something like 50 micro arc second. Also, whatever it is, micro arc second, it's a, you don't have well, the sun is half a degree, right? So micro arc second is tiny spot on the sky. Let's say telescopes in the visible band have resolution which is a fraction of an arc second, maybe 0.1 arc second for Hubble Space Telescope. Well, here the source is not resolvable with visible light telescopes, but I forgot to silence this. The source is not resolvable with visible light, but radio telescopes can reach this micro arc second resolution with whatever techniques. And then some couple of years ago, I don't know if you have seen an image like this. This is the scale of the black hole. We really see this part which is darkened because the light, when it, well, this because of this effect that light is trapped inside. Yeah? So we see a hole in the image. So we can trace the origin of the jet down to the change the font, so I don't know how to silence it. Well, I need to get an automatic gesture for it. So, yeah, we can trace the origin of some source of the size of megabytes down to the tiny region at the maybe vicinity of the black hole. So perhaps the relativistic particles ejected into this directed flow are somehow accelerated close to the black hole. And then, well, the size of this source is about maybe 10 astronomical units or something like this, right? So the difference of the scale is really impressive. And maybe looking at larger, well, this is, yeah, maybe focusing on this, well, how do we know that particles in this relativistic outflow are high energy particles? Again, I come back to the same formulas for synchrotron emission. Then what I see is that, well, this is the radio image of the jet. I see the same jet in optical up to X-rays. So if I make a spectrum of the jet, it would look more or less the same as here, the spectrum of this object. You remember, right? So on occasion here, I would also, well, I see X-rays from the jet. I see radio from the jet. I see it in optical. I can put points somewhere here. I can convince myself that this is synchrotron emission from a population of electrons. And I would apply exactly the same formula to see that electrons populating the jet are something like 100 TeV. And by the way, I can also make an estimate. I can deduce, this is the second formula here. I know the power of synchrotron emission. I know the rate at which electrons are losing energy. I know that these electrons are continuously regenerated all along the jet because they cannot travel from this point to this point, sort of, well, I cannot produce 100 TeV electrons here and transport them there, because while going along the jet, they lose energy on synchrotron emission. So I need to replenish 100 TeV electrons all the time along the jet. What we suspect is going on. It doesn't explain us the origin of the jet, but we suspect that the electrons are replenished in these bright spots along the jet, that are locations of the shocks. Remember this story of supernova remnant that was pushing the shock in the interstellar medium? Particles were bouncing here and there, right? And forming power law spectrum. So here, the jet is a relativistic flow of particles, and sometimes the black hole works more actively, it pushes them faster. Sometimes it is quiet and it pushes the flow more slowly. So there is sort of a permanent, in here on highway, you hear traffic on accordion, yeah? Sometimes parts of the traffic are moving faster, sometimes slower, so they are bumping. Here they are not bumping very often, but there they are bumping into each other, forming shocks. Yeah. So there are shocks here and there in the jet. All these locations, the nodes of the jet, they are perhaps locations of the shocks where particles are accelerated more or less in the same way as in these supernova remnant shells. So high energy particle content of the jet is continuously replenished on the way downstream the jet. Yeah. So then ultimately the jets that are appearing on this map, they are a bit special. These telescopes in the gamma ray band, they are not very sensitive. So if they would see the nearest to us sources like this, radio loud active galactic nuclei, but they would not see further away sources. To see them on the map, we need to do a special arrangement. If we need to sort of, well, if we would look from whatever direction, we would not see the source, but if we align the line of sight along the jet, we would see relativistic particles moving to us. So everything is blue shifted. When it is blue shifted, every photon has higher energy, so the luminosity of the source is also increased, right? So the Doppler effect, it's not only the shift toward the blue or toward the red, it's also boosting the luminosity of the source. So if we have this type of sources, they are called blazars. And in this case, they appear on the gamma ray map. So on the gamma ray map, the sensitivity of telescopes available for us is only sufficient to see these special cases when the jet is aligned along the line of sight. And by the way, this explains why this Doppler effect also explains why it's, no, sorry, I'm going downstream. Yeah, this jet in M87, it is seen one-sided, right? In fact, it is two-sided, but the other side we don't see because it's Doppler, not Doppler boosted, right? This part appears, so it looks like this part of this side of the jet is moving toward us. So the Doppler effect increases the luminosity. So we preferentially see this part of the jet than that part of the jet. For the gamma ray sources, we only see strongly increased emission from the part of the jet, the side of the jet that is moving toward us. Okay, so maybe I would perhaps stop. Right, just for information, I didn't show this picture. So this is for this M87 jet. We clearly see this is the synchrotron bump in the spectrum. That's where we can derive the energies of electrons moving in the jet. But well, if we look at this inverse Compton bump in the jet, we see the inverse Compton emission perhaps up to 10 tera electron volt in M87, right? So this is another way to see the presence of relativistic electrons in the jet. Maybe for today I would stop here, right? So what did we went to this story, two types of sources in the gamma rays, right? So pulsar wind nebula and supernova remnants in the galaxy. And the extragalactic sources are these supermassive black holes that, well, small fraction of them that decided to operate particle accelerators and produce jets. And even it is a sub-selection of this small fraction of all active galactic nuclei with the jets looking toward us. Yeah, that's sorry. So let's stop here. I don't know, some questions, comments? And we make a break, 15 minutes, and we do a couple of exercises. Now it's 10, let's round up to 10:05. Let's meet at 10:20.